Welcome to a brand new edition of Tech2 Talks. I'm Ankit Vengurlekar and I'm joined by a very, very special guest who's come from very, very far, in fact, Professor Raghu Murtugudde. It's a pleasure to have you on Tech2 Talks, sir. Thank you so much for joining us.
Thank you, Ankit.
Raghu actually teaches in the University of Maryland. He's been doing that for about 21 years. And he's here today in the capacity of a climate scientist. And we're largely going to be basing our conversation today around monsoon. One of the biggest seasonal events. We're bang in the middle of it, or should have been bang in the middle of it, but monsoon is pretty elusive this year, like most other years. And so we're going to try and understand from Raghu multiple things around monsoon, largely the science and technology that is used in predicting monsoon output in an agrarian country like India, where agriculture produce is the biggest contributor to GDP. There is this massive amount of uncertainty and unreliability around weather data and information, and how in the day and age of flamethrowers and Elon Musk and SpaceX, if artificial intelligence and machine learning can be leveraged in weather prediction. That's a bunch of questions I'm tossing right at you. Why does this happen, Raghu? Why is there so much of ambiguity around weather information in a country like India?
Yeah, so as a layperson, you can say it's unreliability, ambiguity. But as a scientist, the best term is really uncertainty. And that's basically because the tropical systems have something called convection, where the heating of the land and the ocean, it creates what are called instabilities in the atmosphere. So that instability is typically released into rain, depending on how much moisture is available.
Correct.
So when you do that, these systems can grow so fast in an hour, 2 hours, 3 hours.
Okay.
So compared to, for example, the European weather or the North American weather, where the systems are like 1,000 kilometers big, they linger around for 10 days. So the weather forecast is very reliable for 3 days, 7 days. Even now we are getting up to 10 days because of combining the satellite data, the meteorological weather station data, even data collected from cell phones and so on. Whereas in the tropics, the system is inherently very fast time scale. And this makes the numerical models kind of a big challenge for the numerical models. So we have the best models, we have the best computers, we are building the best observation system, best instruments, best satellites, and so on, even from the oceans. But even after combining them, you can end up with a certain uncertainty. That's a kind of strange word, certain uncertainty, but essentially you predict it, and then because the large scale weather is saying there is an instability coming up.
Right.
And if it doesn't build, what happens sometimes is instead of building over Maharashtra, it's building a couple of 100 kilometers south, a couple of 100 kilometers north. Whereas you're sitting here, you're looking at a weather forecast and you're saying, this is just not reliable.
Correct.
So it's just the inherent difficulty of the tropical system.
Okay, I understand that, just by mere nature of the nature and ecosystem here, convection-based systems are difficult to predict, but it's not just about, hey, oh my God, I forgot to carry an umbrella and I'm going to be drenched on my way to home from work. We're talking about billions and billions of dollars worth or rupees worth, hundreds and thousands of crores worth of agricultural produce. And when there's uncertainty that creeps into farmers' minds about the output that's going to come out, it puts the entire system in a topsy-turvy sort of mode. Will we come to a system where that margin reduces, and how soon will that happen?
No, we are already there. So if you look at the Bombay floods from 2005, the number of people that died, the amount of damage that happened, the number of trains that got stuck, buses, etc. And you look at the 2017 flood. That flood on August 29th, I think, was forecasted 5 to 7 days ahead of time. Okay, so it was slightly off by a day or so, but it was forecasted so well that there is a comparative reporting on that. And we did much better in dealing with that. And it's not just for Bombay. Overall, the floods that have now become much more widespread because of global warming and so on, the mortality has dropped continuously.
Even though the impact of floods has increased, because readiness is getting much better because of predicting this.
The population has increased, and yet we have reduced mortality. Okay, so there is progress, but unlike comparing to Google Go, etc., this is a system that grows very fast. There are rules. We know what the equations that govern the system are. We are solving them, but these so-called moisture dynamics or microphysics, that happens at molecular scale. So we cannot really capture them right now. But that doesn't mean we won't be there in a few years. Considering the increasing computer power that the government of India has invested in at IITM Pune, in Indian Institute of Tropical Meteorology, petaflop machines are coming in, and the grid size of the model that we are solving used to be order 200 kilometers, okay, which means all of Bombay was covered by one grid point. The cloud is never 200 kilometers big, right?
It's highly regional specific.
So now we are solving for weather things at 7 kilometer scale.
Wow.
Okay, that's a huge jump. Are we there yet? Of course not, because eventually you want to go down to something like 500 meters.
Wow.
And will we get there? Of course we will get there.
Is that a global benchmark?
It is kind of where our understanding begins to become a limitation.
Okay.
So the turbulence, etc., we don't know how to exactly solve it like much lower than 500 meter scale.
Right.
So even if we get to 500 meter scale, the forecast will be so good that you have to remember that our expectations keep going up.
Of course.
The better we do, the more people expect.
Right.
So if you do well for 3 days, they will say, but it's wrong on the fourth day or something. So we have to keep up with the expectations. But we are definitely on a trajectory that is headed towards that, and it'll be literally like designer forecasts. You could be calling and saying, I'm going on a vacation to Pune, is it going to be nice next Thursday or tomorrow, or going to the beach, whatever. So we will definitely get there.
How many years till we get there approximately?
I think you will see in 5 years huge improvements
Wow.
at a Bombay scale.
Now, Raghu, for the benefit of a lot of people out there who are not climate scientists, how about you give us a broad 30,000 feet view of how is it that weather movement is predicted? How is weather predicted, or how is rainfall predicted? How do systems do that? How does the meteorological department do that? And how do private partners do that?
At the very basic level, you have the so-called equations of fluid motion. So we know the heat capacity of the water, which is very high, heat capacity of the air, which is much lower, which means the air can get heated very fast, cooled very fast, and it can move much faster. The density is much smaller, water is heavy, and so on. So you start with those things, and then there is something called thermodynamics and dynamics, which means when you heat the air, it can hold more moisture. That moisture can rise, form clouds, clouds can move, they can cool and condense, and can rain. Whereas the ocean is a kind of a slowly warming system that also cools slowly. So if you think about the monsoon, as the sun moves from south of the equator into the northern hemisphere, the land has very low heat capacity, so it will warm up faster than the ocean. So if it heats up faster, the pressure gets lower. So the ocean, which is relatively colder, has a higher pressure. So you move the air from the ocean to land, and then there is rotation of the earth, which gives the winds a certain change in the direction. That's why the winds comes from the southwest into the Indian subcontinent. So that moisture from the ocean is constantly being transported. So it's being forced up the Western Ghats, for example. As the air rises, it expands, cools, the water that's in there falls. So the coast gets tons of rain, and the air crosses over the mountains to the other side. It has much less air. So that's why you have Marathwada, Vidarbha, and so on not getting as much rain as the coastal regions. If I ask you whether December 15th will be cooler or warmer, you'll probably say it'll be cooler. So that's what you expect. That's climate.
Correct.
You expect that December is going to be cooler than June. But weather is such that some very cool air might come down on June 15th, and December may in fact be 15, maybe a warmer day. So that's weather. So climate is what you expect, weather is what you get.
Okay.
When you predict it, that's what you kind of try to do. So weather is a fast moving system, so the ocean doesn't have much to say on a day-to-day basis. Okay? The monsoon system is set up, and then weather is doing its own thing because the atmosphere is moving fast and so on. So the prediction at the climate time scale comes from the fact that the ocean is dragging the atmosphere on slow time scales, like seasonal time scales. So we can do predictions of weather up to 5 days, 7 days.
Right.
And then it gets a bit chaotic. But because of the ocean, you get prediction also at the longer time scale,
Right.
which is a very different system. So the challenge is really to do weather and climate with the same system. How do we create a model? Because remember, weather we are doing at a very high resolution. You are sitting in Bombay and you want to know, is it going to rain in Parel or not?
Exactly.
And if it doesn't rain here, you don't care if it rained somewhere else in Bombay itself. So the other thing there is that the temperature has a very large scale. Okay, all of Bombay may be at the same temperature, but it can be just raining here or there.
Correct.
So you can think of it as a kind of a popcorn kettle, heated up very uniformly, but the kernels pop somewhere,
Individually, yeah.
right? So rain is like that. It's almost like a noise. So it just pops up here and there because of the instabilities. This is why rain is so hard to predict. The temperature predictions, if you look at it, they'll be on the dot. But when the rain is not there, people just, because here people expect to be warm all the time.
Right.
So they want better rain predictions.
Right.
So that gets into difficulties about how much we are limited right now in modeling the clouds, when the clouds rain, and what the dust does to the cloud, what the pollution does to the cloud, how it affects the rain. For example, a lot of pollution provides a lot of so-called cloud condensation nuclei, which actually produces more drizzle than heavy rain. So if it drizzles, then you don't get the heavier rain. So dust and pollution in that sense have this, an impact on so-called cloud microphysics. So all these complications are there, but every aspect of it is making steady progress.
Wow, that's fantastic. I'm pretty sure that's like a 2-year course that you just gave it out here in 5 minutes or something like that. Are there scientific tools that can be used by the government and powers that be to prevent or minimize the amount of loss to life or to property or to livestock that happens? Because it's not a surprise that Assam will be flooded. It's not a surprise parts of West Bengal are going to be flooded. And with climate change, the cyclones and the rains are getting only fiercer. So is there any sort of ray of hope that science and technology can offer?
There is a natural science solution and there is a social science solution. So natural science has multiple levels. The simplest things is to start with permeable pavements, rain gardens, water harvesting structures, etc. But also recovering the upstream damping natural structures like forests, the old abandoned or destroyed hydrological structures which would properly navigate the water to the oceans and so on. Better predictions help as well, right? The social science, in fact, some work from IIT Bombay that I'm involved in that shows that when we looked at the census data from 2001 and 2011, we looked at the natural hazards and we looked systematically at where the vulnerabilities are. And it surprisingly turns out that when women are educated, the families do much better in coping with the disaster and recovering from the disaster, just because they know how to deal with the information better, the weather forecast better, and the warnings better, and take better action than uneducated women. So it's a very significant and very clear suggestion that educating women helps families reduce the impacts of natural disasters. Social science side, obviously helping girls helps a lot, and from the natural science side, predictions and all these mitigation of urbanization, that's very important.
This is a phenomenal revelation. I had no idea about this, and this is great. Help education of girls, help in their development, and it's basically for survival. If you want to survive, just let the girl child get educated. Wow, this is a great correlation. I feel smarter already just with this brief chat with Raghu Murtugudde. Thank you so much for taking out the time. We're really glad that we got you in the midst of Maryland and IIT Bombay. If people want to read your work, if they want to follow you online, where can they catch you and ping you on the internet?
They can Google my last name. I have a huge digital footprint, and the first thing that shows up, I think, is my website, raghu.umd.edu. I also write a lot in all the newspapers, Huffington Post, and so on.
And of course, he writes on Tech2 and First Post. I mean, if there's any big weather or climate-related event, we try and get Raghu to write for us as well. Thank you so much, Raghu, for taking out the time and for explaining us this very, very complex and layered subject in so to say, lay speak. Thank you so much for doing that. I hope you guys enjoyed this edition of Tech2 Talks. We're going to be ramping up our science efforts on Tech2. I'm sure you've realized that. If you go to the homepage, you'll see a lot of cool science stories that Rishi, our brand new science reporter, he's doing as well. So make sure you subscribe to our YouTube channel and share this with everybody, because weather is something that affects all of us. And I think it's cool to know what's going on around you. So make sure you do that. And thank you so much for watching.